Hi, this is Scott Vaughn. In this video on conditional probability and medical diagnosis, I'd like to redo a problem that I've looked at in previous videos, but after seeing this video by Matt Parker, it's this video here where he introduces this Parker machine that's 80% accurate, and he has a lot of fun with this. It's a neat video where he comes out with these presents. They have a lot of fun with this idea that there are 5 phones in these packages of these 100 packages, and they have a machine that is 80% accurate at identifying them. And of course the context is in the same idea of a test looking for it's a more fun way of packaging this idea of a medical diagnosis test. So what I thought I would do here is to work through the numbers that they used in that video and calculate the same question based on those numbers. And then I also have a really neat way of visualizing this result and understanding how it works in that visual way. So that's what I was going to try to do that's different with this video is lay out how to calculate it, and then a visual, use a formula that will be able to calculate this very quickly, and then use that formula to graph and visualize that result. Okay, so the question says, suppose a certain disease affects 5% of the population. Suppose a test used for the diagnosis of the disease is 80% accurate. Number 1, if a person tests positive for the disease, what is the probability they have the disease? And number 2, if a person tests negative for the disease, what's the probability they don't have it? Okay, so to answer those questions, we'll use some notation, some probability notation, and make a table, and we need to clear up exactly what's meant by this 80% accurate. So first, I'll use this notation to say the probability of the disease. That's the probability of the disease. It says it's 5%. It affects 5% of the population, so the probability of having the disease would be 0.05 for a person randomly selected from the population. I'll get back to talking about that more, and that's an important point, but that can also be written as 5 out of 100. Now, this point about being 80% accurate, the way to translate that is to say that the probability that you test positive if you have the disease is 80%. If you have the disease, it will identify that correctly 80% of the time. That's what I mean by 80% accurate. That's what Matt Parker meant by 80% accurate in identifying the gifts in those presents. And so if you have the disease, 80% chance you test positive, then we would say the probability that you test negative, given you have the disease, that would be 20%. Let's group those two together, and then let's say similarly. So then let's also say, well, it's being 80% accurate. If you didn't have the disease, 80% of the time it will show negative, right? So that means the chance that you test negative when you have no disease is also 80%. But that also means the chance that you test positive if you have no disease is 20%. This is what we call the false negative, and this is the false positive. A false negative is when you have the disease and you get a negative result. So it's wrong, it's false, you actually have it, but you could still test negative due to the inaccuracies of the test, right, or the uncertainty in the test itself. And it's possible that if you have no disease, you could still test positive because it has this 20% false positive rate because it was only 80% accurate. So in some other videos that I've done on this, we've had different false positive rates and different false negative rates. They don't necessarily have to be the same, but in this case, when we just state an 80% accuracy rate, the test is 80% accurate, then it's both 80% accurate in saying positive when you have the disease and 80% accurate in saying negative when you don't have the disease, and of course, conversely, 20% inaccurate in both of those false negative and false positive rates. Okay, so now we put all this together into a table to answer those questions. Maybe before I do that, I just want to point out, if you've never looked at a question like this, there's a really important and very basic question at the very beginning, that the question here of if a person tests positive, what's the probability they have the disease? That is different than what's the chance that you test positive if you have the disease, right? The question that we're actually asking here is, what's the probability you have the disease if you test positive? And this question is, what's the probability you don't have the disease if you tested negative? So the chance that you test positive if you have the disease isn't the same as the chance you have the disease if you test positive. It's the same idea in real simple terms. You could say the chance you have a cold if you sneeze isn't the same as the chance you sneeze if you have a cold. They're different. They could potentially be really different. And in this example, they are hugely different. So that's a really important point right at the beginning to make sure that you see that difference in conditional probability. That's what conditional probability is all about. That's why this is such an important example in classes in probability, and really just even understanding the difference is sort of a basic everyday understanding of probability that is really good for everybody to understand. So we can actually get these probabilities using something that's a very sophisticated tool called Bayes' theorem. But for these types of questions where you have only these two, A and B, we have enough. We don't have too many cases, and we can just put it into a table and answer it that way. So you don't have to use a formula to get the answer. You can just use a table, and you can really see how it works out. So I think that's a nice way to do this problem when you're first introducing it, is with this table. So the way I always do the table is I would say we've got the case of somebody has the disease or no disease. And we're going to need a total. We have the possibility that somebody tests positive or negative, and we're going to need totals. So we go back to the very beginning and say, well, the probability of the disease itself is 5% because it affects 5% of the population. We're picking anybody from the entire population, so the probability of the disease, 5%, can be interpreted as an average of 5 people out of every 100. So what you could do with the table is just say, suppose that we had a sample of 100 people, then 5 of them would have the disease on average. So if you put 5 people in this table, this represents the statistical average, right? And then you'd have 95 people that don't have the disease. Now it's possible, that you could have 100 people and nobody has it, and then the next 100 people that you sample, maybe 10 people have it, and so it's averaging out in the population to be 5 out of every 100 on average. And so I'm capturing that average 5 people per 100 in the table. So these tables actually represent averages, really, in the context of probability here. So the way to read this table now is these are people that have the disease. There are 5 of them. But some of them are going to test negative and some of them are going to test positive. And because we had a false negative rate, we know that having the disease and testing negative, this right here is the false negative. These are false negatives. And here is a column for people that test positive, the total number of people that test positive, and here is the row for people that don't have the disease. So this right here is testing positive but having no disease, so those are false positives. So we had false negative rate of 20%, a false positive rate of 20%. And so what you could do is say that if you have the disease, the chance that you test negative is 20%. So we're actually getting 20% of these 5 people. You can do that by just saying 0.20 times 5, and that's 1. And so obviously you have 5 people total, minus the 1 that actually got a false negative. There would be 4 people out of the 5. That is the 80%, right? You could also just do 80% of these people are going to test positive. And so we've got 4 people here and 1 person there that make up this total of 5 that actually have the disease. False positive rate was 20%. So you can take 20% of the 95 people that don't have it. 20% of them are actually test positive, and 20% of 95, that's 19 people. That would be 19 people on average out of 100 would get false positives. And that's a lot, and that's what's the problem. So once you have the total here, 95, you could simply subtract the 19 and get 76. Also, you could just say, well, 80% of these people that don't have it are going to test negative, and so you could just do 80% of 95, and that gives you the same 76. So now we're ready to add these up. This is 23. This is 76 plus 1, so that's 77. You can confirm that the total number of people that actually test positive plus the total number of people that test negative, 23 and 77 makes 100, so that's good. That means I'm doing everything correctly in the table. And you recognize now that you've got a lot of people out of these 23, most of them actually don't have the disease. And that's really a problem with this 80% accuracy, means 20% inaccuracy and a lot of false positives, particularly when it comes to especially now this question, number one. It says, if a person tests positive for the disease, what's the probability they have the disease? Look how many people would actually test positive total. 23. And how many of them really have the disease? 4. So the answer to this is 4 out of 23. And 4 divided by 23 is 0.17. It's 17%. You could have never guessed that if you looked at these numbers just at the beginning. How could you ever do that? You could never get that in your head. Really hard. Anybody could get that wrong. You'd say, like in the video with Matt Parker, how you have this sort of idea that the 80% accuracy means you're going to get 4 out of the 5 presents that are the winners out of the 100. Well, yes, there is 4 out of the 5 that are correctly identified, but there's also 20% that don't have that don't have the disease that are incorrectly identified, and that just was just really hard to do, mentally and to really grasp unless you have really a lot of training in probability. So 17% is very low, right? So how could that be so low? Because of all these false positives. That's why. I will also interject that number is low because the incidence of the disease is relatively low, 5% out of the population. 5% of the population has the disease. So you wouldn't really want to give everybody in that population there a test that was only 80% accurate, right? Because what we've just seen now is that if you actually test positive, the chance that you have the disease is only 17%. So it's really pretty much useless, right? 80% is just not accurate enough under the circumstances when you have only 5% of the population having this particular disease. So you'd have to have a much more accurate test. So I'll get that some more later in this video. Okay, let's look at question number 2. If a person tests negative for the disease, what's the probability they don't have it? So in our conditional probability notation, we would say if they test negative, what's the probability they don't have it? So we're looking for probability of no disease given negative. Right? So how many people tested negative? How many people tested negative total? That was 77. And how many of them don't have the disease? That is 76. And that comes out to be 0.987, or let's just round it off to say 99%. So there's the answer for that one. So these are not complements of each other, right? Just because this is 17% doesn't mean this should be 83 or this should be 1%. They are just completely different events, right? Given you tested positive, what's the chance you have the disease? And given you tested negative, what's the chance you don't have the disease? The reason the chance of not having the disease is fairly high here is because there aren't that many people that actually had it out of 100. And if you're just testing a randomly selected person in that population, there's a good chance they don't have the disease. And testing negative just makes that even more likely. So what I thought would be interesting to look at next is that if we just could change the accuracy of the test and change the percentage of the incidence of the disease in the population and look at how these results change, that's what algebra is for. So let's do that. So I'll define some variables. I'll say S is the sample size. It could be a population or any sample from a population. It's going to be the total in the table, right? The total number of people that are sampled that either represents a part or an entire population, right? And then we'll do this variable D to be the incidence rate of the disease. And that's a value that will be between 0 and 1, so that 0 means that the disease doesn't occur. If it's 0.05, then the incidence rate is 5%. If you are at 0.5, you would have 50% incidence rate of the disease. Half people have it and half of them don't. And all the way up to 100% incidence. Everybody has that particular disease or whatever it is. It doesn't really have to be diseases that this could be applied to. And so let's do one more variable, that is the accuracy rate of the test. And that's also between 0 and 1. So the test could be up to 100% accurate, or it could be all the way down to 0% accurate. That's funny sounding, but it's possible there with the math that we could choose any level of accuracy. We could imagine 99% accurate, 99.9% accurate, 100% accurate, or so what I want to do is create a graph where I have a slider where I can change the accuracy of the test, I can change the incidence rates of the disease, and look at these probabilities that I just worked out. But watch how that changes as those numbers change. So we need to make a table, as we did before, so I can figure out what the probability is. If you tested positive, what is the chance that you have the disease? That's really what this whole thing sort of, comes down to. So we'll do the same table as before. So there's disease and no disease, and there's a total. There are people that test positive and test negative, and a total. But now we have an arbitrary sample size, S. And so if, let's say, 5% of the population has the disease, then you would multiply D times S. So let's say that's D times S here. And if, let's say it was a 5% disease rate, incidence rate, then it would be a 95% chance of not having the disease, and so this would be just S times the quantity 1 minus D. Right. So maybe it's 25% of the population has the disease, and then so that would be 0.25, and this would be 1 minus 0.25. This would be 0.75. 75% don't. Right. So these are complements of each other. And as before, this is the false negative. These are people that have the disease. In this box, we would say you're in this row, has the disease, but you tested negative. So we need to figure out, how do we identify the number of people that are false negatives? Well, what you could do is first just figure out, how do you identify, it's based on the accuracy of the test, which is this value A. And so, so it's going to be the total number of people that are in the population times the total number of people that actually, the fraction that actually have the disease times the accuracy of the test. You could rearrange those letters as SAD, S-A-D, and that would be really fitting because it is testing positive and actually having the disease. So they would be the people that are SAD for sure in this context. But let me say it again, like we had, basically, if this is the number of people that actually have the disease, I would multiply by the accuracy rate. Like maybe it's 80%. So 80% of these people that have the disease, they test positive. So it's the total number of people that have the disease times the rate, the accuracy rate. So if the accuracy rate is A, then sort of the inaccuracy rate is 1 minus A. So this would be S times D times the other fraction, the complement of the accuracy. So this would be 1 minus A. And down here we have people that test positive but don't have the disease. These are false positives. And how do we compute that? So it would be, so maybe I can say it like this. So what I could do is I could take this number right here and multiply by the accuracy. So this would be S times 1 minus D times A. Because this accuracy rate represents how many people would actually test negative out of those people that don't have it. That's what that number would be right there. And so it's just the complement of that number, 1 minus A, that has to go into this box. So this is S, 1 minus D, and 1 minus A. So, of course, now we need to add these two together, and I did that separately on a piece of paper, and I've worked that out. That's going to be S times 2AD minus A minus D plus 1. That's just a great little algebra exercise, right? To take this quantity, multiply it out, add them together, collect like terms, and write it like this. And do the same thing over here. Add these two quantities together to get the total in this box, and what you get is S times A plus D minus 2AD. Now, we could check that this is right, just like I did before. What I could do is say, if you add these two together, you should get this quantity. So let's say if I'm adding those together, I could factor out the S and add what's inside. And the 2AD and the minus 2AD, they cancel. Minus A cancels with A, minus D cancels with plus D, and there's only a 1 left. So you have S times 1 gives me that S there. So this is correct. Okay, so now let's get back to the questions. Let's say if you test positive, what's the probability you have the disease? We write that succinctly. In math notation, we say the chance you have the disease if you test positive. Well, how many people are going to test positive? That's this number right here. So put that on the bottom. Total number of people that test positive is S times 2AD minus A minus D plus 1. And how many people of those that tested positive, how many actually have the disease? It's this number, S times D times A. So we put that on top. S times D times A. So now you can see it wouldn't really matter what size population we have or what size sample we have of the population. That cancels out, and we can just write this as A times D over 2AD minus A minus D plus 1. So now we can put that into a Excel spreadsheet or into Desmos and actually look for a graph of that. That's a function of two variables, so that's even a topic there, right there in Calc 3, where you can look at the surface that's generated if you have an x and a y value and you have the probability as the z value, but won't do that here. I have another just two-dimensional way of looking at it. So we get the other, just like I did in the previous example, where you say if you tested negative, what's the chance you don't have the disease? So no disease given negative. How many people test negative? It's this box here. Total number that test negative, right there. And how many of them don't have the disease? That's that number there. So, of course, you can see the S's are going to cancel. So I'll just write that as, on the bottom, I have A plus D minus 2AD, and I cancel the S. And on the top, I have A times 1 minus D. And yeah, we can graph that as well. So that's what I did. Okay, so here's the graph in Desmos. And what I have first is the incidence rate of the disease. That's something you can interpret as a percentage. So this means 5%. It means 5% of the population has the disease. If you were testing, if you picked a person at random from the entire population, there's a 5% chance that the person has the disease. That's the way to think about that. And this is the accuracy rate. I have it set right now on 80% accurate. And here is that probability that we were just calculating before, and it comes out the same. What that represents is the chance that you have the disease if you test positive. It would be 17%. Now that's awful, right? It makes the 80% accuracy is just not good enough when you only have 5% of the population having the disease. And this right here is the chance that you don't have the disease if you tested negative. It's at about 98.7 or 99%. Now I can graph this other one in a minute. I'll come back to that, but there's a lot on the graph to try to wrap your head around and understand. Like, what does this, how did I come up with a picture like this? So what I was thinking was, along the horizontal axis here from 0 to 1, this is the accuracy rate. So the further you move along here, the increasing the accuracy up to 100%. And then the vertical scale is the probability that you actually have the disease if you tested positive. Right? So it's going up to 100% probability with 100% accuracy. If it was 100% accuracy and you tested positive, then there's a 100% chance that you actually have the disease. So this vertical scale, think of that as a probability on the vertical, and it is the probability that you actually have the disease if you tested positive. So if we increase the accuracy to 99%, So 5% of the population has the disease. The test is 99% accurate. There's an 83 or 84% chance that you would actually have the disease if you tested positive with that test. So then another interesting thing to do is to manipulate the incidence rates of the disease, because even that is a little bit low, like even 99% accurate. It's pretty confident, but what you would want to do is say, well, does this person have any symptoms? Because this is still not certain that they actually have the disease, even when they tested positive. This is 84% chance that they have disease. So what happens is if you could just give the test to a smaller population where there's a higher incidence rate in that population, so how does that affect the graph? So that's kind of an interesting effect on how that bends there as we increase. So if we had a larger percentage of the sample that actually have the disease, then we can be more confident in those results if the test gives us a positive. So this would be, for example, I might imagine, somehow to explain this would be like, well, you would give that test to people who were exposed to the disease, or they have symptoms, or they have some reason to suspect. I think, this obviously I'm thinking the whole time I'm doing this about COVID-19, but this is general for any test. If the person has a genetic background, has concerns, and talked with the doctor, and it's so now the test is used to say, well, first we're going to screen for whether it's actually reasonable to use the test. And so there's a larger percent of people that have this genetic background or these symptoms or whatever the circumstances are, that increases the probability of having it among the people that are sampled. And so then you can have a lower accuracy test and still be pretty confident, right? So you could say, for example, if we change this now to 80% accurate, test is still 80% accurate, but we're only testing people that were pretty more likely to actually have it. Now that 80%, it's pretty useful. Now there's a 92% chance that the person actually has the disease if they tested positive. So interesting to sort of think about how that works, and it's kind of neat to look at this sort of concavity of the curve and how that changes. And I think we're looking sort of at level curves of the surface, but let's bring this down to like just 1%. Suppose there was only 1% of the population that has the disease. Now you have to be extremely accurate in that test. I mean, actually, even a 99% accurate test, if you tested positive, there's only a 50% chance that you actually have the disease, because it's such a low incidence rate of the disease. If only 1% of the entire population has the disease and your test is 99% accurate, it's pretty much worthless, because there's only 50% chance that the person actually has a disease if they tested positive. Right? So I'd have to increase this up to 99.999% accurate to get up there into an interval where it was be more confident the person really has the disease if they tested positive. Here I've zoomed in just a little bit in Desmos so that we can now sort of pick up these little marks that say 20% probability, 40%, 60%, 80% probability, and here is the level of accuracy of the test. And so I can see now when you are testing among a group that it is more likely that the disease is occurring among that group, then you can have a much less accurate test and be more confident with it, right? I mean, maybe some of those observations are kind of obvious, but this is kind of a neat way to use some algebra and the graph to really visualize that result and to see those numbers changing dynamically. So then the other thing that I did was to graph that other probability, that probability now that you don't have the disease if you test negative. And as I change the incidence rate of the disease, it's kind of interesting to see how those two are symmetric to each other. So now if I set the numbers back to 5% incidence rate of the disease and 80% accuracy, I can still be pretty confident if somebody tests negative that they don't have it. It's up there at 99% basically, or 98.7% chance that if they tested negative, the probability they don't have the disease. And I guess we can see how you can reduce, you can have a lower accuracy of the test and still be fairly confident when it says negative, fairly confident the person doesn't have the disease still, even as the accuracy of the test drops in that situation where the disease is not very prevalent. But as I increase the prevalence of that disease among the population, oh, there's another interesting point right there at 50%. It's kind of interesting to see, like, now I realize that the probability that you have the disease if you test positive exactly matches the accuracy rate. If half the people have it and half the people don't. I don't know if I would have really recognized that if I didn't have this animation to see that. And of course the chance that you don't have the disease if you test negative is also exactly the same as the accuracy of the test. So that's kind of neat little discovery there that I can just visualize. And so I was going to say, let's suppose that it's at this level of 80% accuracy, but we're testing in a group where there's a higher chance that among those people that we give the test that they actually have it. So let's say that it occurs among 80% of those people. Well, if you test negative now, there's a 50% chance that you don't have the disease right there. That doesn't seem very helpful at all. So, yeah, I guess the conclusion is sort of like I'm less trusting of the negative result when there's a high percentage of people in that group that actually have it, right? So I need to have more accuracy to get that number up there into, up to the, hot, closer to 100%. Maybe just one other observation to sort of an extreme case of 0% accurate, right? Suppose we had 10% of the population has the disease in a test that's 0% accurate. So then the probability that you have the disease if you have a positive result is 0, and the chance that you don't have the disease, given that you got a negative result, also 0. It's because both the A shows up in the numerator in both of these, and so it goes to 0. With 0% accuracy, the probability of basically a correct result is 0. Yeah, I guess I sort of stumbled on the words that sort of express what that really is. It's sort of like curves that represent the probability that it's getting the right answer based on the accuracy, right? So as you increase the accuracy, you can see the probability that the test is giving you the correct answer increasing up there to 100%. And really just fascinating to think about how those two flip as the percentage of the population that has the disease increases, how those two are complements in a way, or they're reflections of each other in a way. I mean, on the one hand, like for example, with this, let's say, let me put it on 20% of the population has the disease, and the test is, let's say, 90% accurate. Well, if you test positive now, there's a 69% chance that you have the disease, and if you test negative, there's a 97% chance that you don't have it, and these don't add up to 100%. They are not complements of each other, but I can see how they follow curves that are kind of reflections of each other. That's another way of just looking at that idea. Yeah, interesting. Okay, so that's it. That's the end of the video. I hope it's been interesting and useful. And thank you for watching.